Hi dear friends, in this session we are going to discuss about assignment problem. It is a subset or special type of transportation problem. Coming to the learning objectives, after this session you should be able to formulate a problem as an assignment problem known as or abbreviated as AP, solve an assignment problem by using a method known as Hungarian assignment method, that is HAM, understand the special cases of an assignment problem. Coming to the nature or structure of the assignment problem, an assignment problem is a special type of problem where the objective is to assign a number of origins equal to number of destinations at a minimum cost or maximum profit. So let us take in this way. Assume that you have three persons. Let us say P1, P2, P3. And you have three jobs, J1, J2, J3. You know the cost of assignment of a particular job to the particular person. Then how best you can assign the jobs to the persons is the discussion here. So in other words, you will be having some persons and you will be having equal number of jobs. So you are supposed to assign one job to one person at the minimum cost or maximum profit. The assignment problem is solved by a method known as Hungarian assignment method, HAM. Let us understand the general formulation or generic form of an assignment problem. Let us say you have m persons, P1, P2, P3 and so on up to Pm, and equal number of jobs, J1, J2, J3 and so on up to Jm. Let C11, C12, C13 and so on up to Cmn are the costs of assignments. Then the problem is structured as shown, that is P1, P2, P3 and so on Pm, J1, J2, J3 and so on Jm are the jobs. Okay, so these are the costs of assignments. Based on these costs of assignments, you are supposed to assign best job to the best person so as to minimize the cost or maximize the profit. That is the objective or the concept of assignment problem. Now let us take a numerical to understand how to use HAM or how to solve an assignment problem. Solve the following assignment problem wherein the cell entries represents the cost of assignments. If nothing is given, you have to assume that they are the costs and the objective is minimization. Okay, person to the jobs, like let us say this is P1, P2, P3, J1, J2, J3. Fine. Now 18, 17, 16, 15, 13, 14, 19, 20 and 21, they are the costs. Okay, the Hungarian method, so we'll understand in the steps. First of all, before applying the Hungarian method, you have to ensure one condition, that is whether it is balanced or not. So in case of assignment problem, whenever number of rows is equal to number of columns, that is if it is square matrix, the problem is stated as balanced problem. The problem is assignment problem, balanced assignment problem. Hence Hungarian method can be used to solve. Okay, if not, you have to balance, that will become a special case. We will discuss in the later stage. Fine. Now number of rows is equal to number of columns. Okay, hence you can apply the method. In other words, it should be square matrix. The concept is if you have three jobs, you should have three persons to perform. It is like that. Now the procedure is very simple. First thing is you have to go for row reduction. So what is this row reduction is? In each row, you have to select the least element. You have to subtract all other elements from it. Okay, that is called row reduction. Okay, select the least element or minimum element in each row and subtracting. Okay, subtract the other elements of that particular row. Okay, by doing this, so for example, if you take the first row, so 16 is the least element. 18 minus 16, 17 minus 16, Okay, 16 minus 16. So like this, for all the rows you have to perform. Okay, this one and all. Fine. That becomes row reduction or step 1. Step 2 is same thing you have to apply for the columns, like, okay, selecting the least or minimum elements in each column and subtracting the other elements, like for example, if already there is 0, no need to operate. Even if operate, you will get the same thing. Like in this case, no, so each column is also having 0. Hence, even if you operate this column also, you will get the same result. Fine. It's a coincidence, of course. So please see that, okay, after step 1 and step 2, no, so each row and each column will be having at least 1 0. See, you can see here, now this is reduced row reduction as well as column reduction you have done. First row, second row, third row, first column, second column, third column. So this is called reduced matrix. I mean, the matrix obtained after step 1 and step 2, no, is called reduced matrix, which is ready for allocations. Allocations, okay, we are going to discuss now how to assign or allocate. So very first step is row reduction, then column reduction. So after ensuring that each row and each column is having at least 1 0, which is nothing but reduced matrix, you have to go for the third step, allocations. So the step is scan the elements, or scanning the elements row wise and assigning for 0 in a row having single 0. Okay, cancelling this one, like, okay, let me explain like this. So for example, first row, how many zeros it is having? 1 0. So what is the meaning of 0 here is relatively this is the better position. Okay, so hence you go for assignment there, or to assign there. So that is the purpose of, okay, creating or getting the zeros by using these two steps. For example, here you know that the least cost is this one, so you can assign directly, but okay, so if you have the 0 reference, it will be easy. That is the reason. So why you first have to get the reduction matrix, then you have to go for assignments. Okay, first row, no, how many zeros? Single 0. If by chance if you have 2 zeros, you leave it. Okay, so you put square bracket for that. If you are scanning row wise, no, you cancel the column. Second 1 0 you have, no, okay, so you are scanning row wise, you cancel the column. Third, you are having single 0, you scan the third row like this, and you capture this or you assign for this, so you cancel this. Okay, now what is your observation is, so whenever number of allocations is equal to order of matrix, no, whenever number of allocations is equal to order of matrix, so you can say, so you have got the optimality, or the solution is optimal. See, so number of allocations means this one, zeros allocated 1 2 3. So order of matrix is 3 cross 3. Hence you can declare the optimality and you can write the assignments. Okay, the other way of declaring the formality is when number of cross lines is equal to order of matrix, no, then also you can say it is optimal. So they are one and the same. Number of allocations means number of lines, no, fine. So okay, now once if you get number of allocations is equal to order of matrix, you can write the assignments. Assignments means you are suggesting to assign person 1 J3, person 2 J2, person 3 J1, like. So this is the optimal assignment which will minimize the cost to the company or organization. Fine. So just, okay, how I am writing this? This one, allocations, nothing else. Now to obtain the optimal cost, no, these are the allocations or assignments. So you have to go back to the parent or original matrix. P1 to J3, what is the cost? 16. P2 to J2, 13. Then lastly P3 to J1, that is 19. This is called assignment cost. Okay, 16 plus 13 plus 19, that is 48 units or 48 rupees, whatever it is. Fine. So this is the assignment schedule and this is the assignment cost. Okay, so let us quickly glance what you have done. First, okay, row reduction, then column reduction. Once, okay, you get at least 1 0 in each row and in each column, no, that is called reduced matrix. In other words, after step 2, no, so you will get the reduced matrix which is ready for allocations. So you have to scan the elements row wise like this. If you have single 0, you have to capture that like this and cancel the opposite column. So like this, second row here, when you are scanning row wise, no, you have to cancel the column. Third one, like this. Fine. And okay, if at all, if you have more than 1 0, what to do? You will see in the later stage. And okay, you can see here, so person also is not repeated, job is also not repeated, because the basic thing is each person should be engaged or each job should be assigned. Okay, So no person is given the 2 jobs, or no job is repeated, or so. Fine. Now let us take one more simple numerical. 4 projects are to be done on 4 different machines or computers. The cost may be in thousands of rupees for computing or performing pth job on cth computer is given below. Assign the projects to different computers so as to minimize the total cost. Okay, you please see the problem. There are 4 projects, P1, P2 and so on. There are 4 computers. These are the costs of assignments. And okay, if nothing is given, you have to minimize. I said no, let us go for minimization. As the number of columns is equal to number of rows, no? Okay, the problem is a balanced assignment problem. You can proceed for method, that is Hungarian method. So step 1, row reduction. So as we discussed in the previous problem, identify least element in each row, subtract all other elements from it. Do it for all the rows. Okay, this is reduced matrix, row reduced matrix, what I can say. Same thing you have to do it for columns. So identify the least element in each column and subtract it from other elements, like. Fine. So you can see this after step 1 and step 2, each row as well as each column is having at least 1 0, which is ready for allocations. So this matrix is known as reduced matrix. Now third step is okay, allocations. Okay, allocations procedure is same. Scanning the elements row wise and assigning for 0 in a row having single 0 and cancelling the respective column we get. Okay, for example, first row, 2 zeros you have, time being you leave it. Second row also 2 zeros you have, okay, leave it, time being. Third row 2 zeros you have, leave it, time being. So I mean you have to find a row having single 0 preferably. Okay, if you have 2 zeros in the first run, you leave it like this. In the second run, let us see that. Okay, this you have to capture first. Okay, once if you see like this, this is to be assigned and this is cancelled. That's what is done here. Okay, then you come back to the second run. Okay, so whichever is cancelled, that you should not take into account. Fine. Now again, if you come to the second run or second round, so this is having 2 zeros again. This is having 2 zeros. Okay, this is having 2 zeros, but it is cancelled in the this one first round of allocation. So hence this is not to be counted. This you have to capture or you have to assign. Okay, so as you are scanning like this, you cancel this column. Fine. Now this is exhausted. This is exhausted. You are left with first and second. Okay, now come back to the third round of scanning. It's quite interesting. Fine. So in the third round, this is cancelled. That is not to be taken into account. This is cancelled. See, after this allocation, this is cancelled, and you are left with this 0. Fine. You cancel this now. Fine. You allocate row wise and cancel this. Now you are left only with this one, it seems. Okay, then automatically it will take the assignment. Okay, you enclose this 0 in the square bracket and cancel the respective column, like. Okay, now so what you can see is number of allocations. You count the number of allocations 1, 2, 3, 4 equal to order of matrix. Hence the solution is optimum, we can say. It is very simple. You have to read the steps, that's all. Okay, you have to scan the elements having single 0. First row wise you have to go. So if you find none of the rows are having a single 0, then you will see what to do. Fine. But here, so first row had 2 zeros, 2 zeros, 2 zeros, but this was having single 0, no? Hence we captured assigned for this. So we have cancelled this. In this process, this is getting cancelled. Hence, okay, you will get one more row having single 0, so that you can check in the second round of scanning. Like this, okay, 2 or 3 rounds or 2 or 3 runs, okay, you have to go. Fine. Now, once, okay, if this is assigned, P1 to C2 you are suggesting, P2 to C4, P3 to C1 and P4 to C3. So, cost, okay, is automatically you will get it. You have to go back to the original matrix and you have to get it. Now, let us take one more numerical. So, 4 professors are each capable of teaching any one of the 4 different subjects. Okay. So, assume that, okay, I have 4 different distinguished professors. Okay. One subject they have to take. Fine. Class preparation time in hours, okay, for different topics varies from professor to professor and is given in the table. Each professor should be assigned only one subject. Okay. Find the schedule so as to minimize, please underline this, minimize the total subject preparation time for all the subjects for all the professors. Fine. Okay, now, okay, it's balanced first of all. There are 4 professors, 4 subjects now. Hence, so it is 4 by 4, in other words, square matrix, or whenever number of rows is equal to number of columns, you can say that it is balanced problem. You can proceed. Okay. Now let us see first this one, row reduction. Same thing I think is needless to explain. Identify the least element in each row and subtract it from other elements. Same thing you have to do it for columns. Fine. Okay, this is column reduction. After first two steps, no, this is called reduced matrix. So okay, and you can allocate for the reduced matrix only always. When none of the rows are having single zero, that's what, then consider the column having single zero for the allocations and cancel. Okay, let us see. First row, no, single zero. Okay, that's what you have assigned, you cancel. Second row, single zero. Fine, you cancel this. Third row, you have two zeros. Third row, two zeros. Fourth row, no zeros because this is cancelled, no? So in the process of assigning this one, you cancel this column. That's what, okay, when you scan the element row wise and allocate, so you have to cancel the respective column. First row, you have cancelled this column. Second row, okay, you have allocated. Third row, what is happening here is, okay, two zeros. When you have two zeros, I told to just leave it for some time. Then, okay, go to the fourth row. Fourth row is not having any zeros because this is cancelled. So that's what, when none of the rows are having single zero, then consider the column having single zero for the allocation and cancel the respective row. Okay. So it is not that, okay, simply when you have two zeros in a particular row, you have to go to the columns. If you get a condition that or status that none of the rows are having single zero, then only you have to go for the columns having single zero or so. Fine. Now, okay, first column is cancelled. Second column, okay, it is assigned, it seems. Okay, you cancelled this way. Third column, no. Third column, please observe that you are seeing like this, not like this. Third column. So you capture for this. When you are seeing or scanning column wise, no, you have to cancel the row. Okay. So it's opposite. When you are scanning and allocating column wise, you have to cancel the row. Fine. Now that is done. So what is our observation after this is number of allocations is equal to 3. That's all here. 1, 2, 3. But order of matrix is 4. Hence the solution is not optimum. Please note that to declare optimality, always number of allocations should be equal to order of matrix. But it's not happening here. Then what to do is, okay, there is one step extra here. So that is called modification of the reduced matrix. So after first two steps, you will call that as RM. So you have to modify the reduced matrix, that is called MRM. Okay. So this, okay, please try to understand. First row single zero, you have cancelled. Second row also you had single zero, you cancelled. And when you come to the third row, two zeros. Okay, when you have two zeros, you have to leave it, I said. Fourth row, okay, because it is cancelled in the first iteration itself. Okay. So hence you cannot consider that. None of the rows were having single zero, then you have gone for the columns. First column exhausted, second column exhausted, I mean it is cancelled. Third column, no, you have seen column wise, so you have assigned for this. When you see column wise, you have to cancel the row. Okay. After all this exercise, your observation is number of allocations is not equal to order of the matrix. Fine. Hence the solution is not optimal. Okay. But that is not the final solution. You have to make it optimum. For this, the extra step is modification of the reduced matrix. If you get this condition, so what you have to do is you have to modify the reduced matrix. Okay. So in this, the process is like this. Identify the least uncrossed element. Okay, that is 1 in this case. Okay, let us see. Identify the least uncrossed element. So here the least uncrossed element, I think it is 2. I'm sorry, it is not 1. Fine. Identify the least uncrossed element. Add this element to the double crossed elements and subtract it from other uncrossed elements. Just these 3 steps you have to follow in modifying the reduced matrix to modified reduced matrix, that is MRM, RM to MRM. So first you have to identify the least uncrossed elements, that is 2 in this case. Add this element to double crossed elements, okay, and subtract it from other elements. In the sense, okay, only this portion, no, okay, this is 2. So you have to add this 2 to double crossed elements. Okay, wherever there is a vertical and horizontal line, no, that is double crossed, you have to add this element, and you have to subtract that from other elements. That's all. 2 steps you remember. So identify the least uncrossed element. You add that element to the double crossed elements and subtract that element from the other uncrossed elements. Okay, other uncrossed elements means, for example, 2 minus 2, 5 minus 2, 5 minus 2, 4 minus 2. And if they are single cross, no, if nothing is given, okay, nothing is given, so hence you retain them as they are. Okay, I'll repeat. Identify the least uncrossed element, add that to double crossed elements, subtract from other uncrossed elements. Okay, if you apply, so the steps that I've explained, least uncrossed element is 2, that is step 1. Okay, add this 2 to this double crossed elements, that's all, 2 and 3. Okay, 2 plus 2, 3 plus 2 it will become. Okay, fine. And other 4 elements, uncrossed elements you have, no, you subtract this 2 from these 4 elements, that is 2 minus 2, 5 minus 2, 5 minus 2, 4 minus 2, 5 minus 2, 5 minus 5. And if they are single crossed, you retain them as they are. Fine. By doing that, so let us see what is happening. Fine. Fine. Okay. This is nothing but the modified reduced matrix, and we have allocated also. How we got this 0, 8? Let us see the first row. 0, 8, 2, 3, 2, 5. This have subtracted 2 minus 2, 5 minus 2. That is 3, no? Fine. Like this. Now, so assignments, okay, you have to do it. First row, 2 zeros, okay, you leave it. Second row, no, single 0, you capture it and cancel it. Okay. Third row, 2 zeros you have, you leave it in the first run. Fourth row, single 0 you have, you scan row wise, cancel the column. Fine. That is first round of this one. Then come back to the second round. Fine. Okay, this is cancelled or something, no, this is cancelled. Hence, so you will be having only this one. Okay, because in the process of assigning to the fourth row, this is cancelled. In the first row, you will be having only single 0 now. This is not to be counted because this is cancelled. So you can, I mean, you allocate for this, you cancel. So like that you have to repeat. This procedure is same like in the previous problem. Fine. Okay. So what is your observation here? After modifying the reduced matrix, you are seeing that number of allocations, that is 1, 2, 3 is equal to order of the matrix. Hence the solution is optimum. Number of allocations is equal to order of the matrix. So you have to give the allocations like this: P1 to S3, P2 to S2, P3 to S4, then finally P4 to S1. And if you want to know the cost, no, just you have to go to the given matrix, you have to map. Okay, this one, P1 to S3. You are not supposed to add these zeros, then you will get 0 only the answer. No, because what is the meaning of assigning for zeros means, so relatively they are the better positions or of less cost. Okay, that's why we created the zeros, nothing else. But original matrix you have to take to find the cost. Fine. So that's what is given, and the respective cost, no. So 9. How we got this 9 means, that is P1 to S3 was 9. You can check it. Fine. So like that 4, 11, 3, and the total preparation time is 27 hours. Fine. So that's what reduced matrix and this one. Okay. So you can see how to convert the reduced matrix to modified reduced matrix before allocations. No. So I have given the steps. Okay. Only thing is here you have to make it 2. No. So this is reduced matrix. This is this one, modified reduced matrix. And of course you have to take this as the reference for this. Okay. Which one? This one, because you have to add the least element to the double crossed element. You have to subtract it from single crossed, uncrossed elements, and you have to retain all other elements. Okay. Now special cases. Let us discuss the special cases. One special case 1 is unbalanced problem. Okay. Always the problem should be balanced to use the Hungarian method. Sometimes the problem may be unbalanced. Okay. Number of rows may not be equal to number of columns. In such cases, okay, you have to balance by adding a dummy row or dummy column. Okay, what is unbalanced problem means? Okay, if number of rows is not equal to number of columns, that is stated as unbalanced problem. You have to understand. Prohibited route, it is very simple. Of course, so it is discussed in the transportation concept also. The allocations or assignments should be avoided for such locations. So I mean a particular location, no? For example, they will give dash or infinity or m here. I mean you are not supposed to allocate for that. That is the meaning. You have to leave it blank, nothing else. Fine. That is called prohibited case. Fine. Unbalanced, prohibited, then maximization problem. Sometimes, no. So of course, assignment transportation cost means you have to minimize. Same algorithm or same method, no, you can use for maximization also. If at all, if the objective is to maximize, it should be converted to the minimization form. Always you please note that. So standard form means minimization form. Okay, if it is given to maximize the profit or so, by using assignment technique, what you have to do is, so one step, okay, you have to perform extra in the beginning itself. What is that is, to convert a maximization problem to minimization problem, subtract all the elements of the given matrix from the highest element, okay, of that particular matrix, then the same procedure could be used. Okay, so we'll take a numerical covering all these special cases, okay, after this. So okay, so this you have to remember. Identify the highest element of that particular matrix, subtract all other elements from the highest element, then it is equivalent to minimization or standard form, I can say. And the last one is alternate optimal solution. Sometimes, so you may be having 2 or 3 solutions which will be giving the same cost, no, then it is called alternate optimal solution. Like, okay, for example, if you want to reach from A to B, 2 routes, okay, may give the same distance, 100 kilometers exactly, then we can say that the problem is having alternate optimal solution. So sometimes is also referred as a multiple optimal solution. These 4 are the special cases. Unbalanced, I mean number of rows is not equal to number of columns, then you have to balance it accordingly, adding a dummy row or dummy column. Prohibited means just you have to skip that location, nothing else. Maximization means you have to convert into minimization by this extra step and you have to proceed. Alternate means, okay, problem may have more than one solution. Like, now just to create interest in the class, I have articulated or formulated this problem. It's very nice. Okay, a group of 5 boys and 4 girls are planning for a one-day picnic. The extent of mutual happiness between the couples, that is boys and girls, when they are together is given in the following matrix. Data has been obtained from their previous experiences. The problem is to decide the proper matching between the boys and girls during the picnic, which will maximize the sum of all the mutual happiness of the couples. Who will be the spectator? So let us read the problem once again and see the matrix also. Please don't take me otherwise. Okay, I have told just to create the interest, or I mean in the sense of articulated this problem. There are 5 boys, 4 girls. Okay, if you couple this boy to this girl, okay, this is the mutual happiness. I mean some points they have given to that couple. So always happiness, okay, you have to maximize, no, that's what is given, like together is given in the following. Data has been obtained from the previous experience. The problem is to decide proper matching between the girls and this one, boys, to maximize the sum of mutual happiness. So assume that there are the profits or the something like points or something like, always you have to maximize, no, B1 to G1, 11, B1 to G2, B1 to G3, B1 to G4, like, fine. So you have to maximize. First of all, you have to observe the nature of the problem now. Okay, there are 5 boys but 4 girls. Number of rows is not equal to number of columns. Hence, it is not balanced problem first of all. Okay, you have to balance it. Okay, we have discussed what special cases. No, in that special cases, the first one is unbalanced. Whenever number of rows is not equal to number of columns, it is unbalanced. You have to balance it. Now, what to do? Only 4 girls are there, but 5 boys are there. You have to assume a dummy girl, like, okay, in the sense you have to create a column here, so that number of rows will be equal to number of columns, or order of matrix will be square. Fine. So that if you write dummy here, you have to write only zeros for that. Just to apply the method, no, we are balancing. Of course, there is no girl at all. Okay, so you are assuming a dummy girl. So with all zeros as the elements, like, fine. I mean the numbers. So so number of rows becomes number of columns equal to number of columns. Okay, there is one more variation here. What is that one more variation? Maximization it is. Just now we have discussed when it is maximization what to do, like, okay, you have to subtract all other elements. So this problem you can do either way. First you can balance, then you can convert into minimization, or first itself you can convert into minimization, then you can balance. Either way it will be the same, I have verified. Fine. Highest element in this, okay, you have to see. So maybe 13 it seems, no? 13. So all other elements you have to subtract from 13. 13 minus 11, 13 minus 3, 13 minus 5, 13 minus 8, and so on. All this. Fine. Then you have to add dummy column. Fine. So by doing that, see, the given problem is maximization problem. Okay, hence first convert into minimization problem. That is, select the highest element and subtract all other elements from that element. Moreover, as the number of rows is not equal to the number of columns, the problem is unbalanced. To make it as balanced problem, add a dummy column. Okay, then we get, see, after the first 2 steps, I mean, we have converted this into minimization and we have added the dummy row. Now it is what? Minimization form and also balance type. Fine, standard form in other words. Okay, so number of rows is equal to number of columns. So the allocations for the reduced matrix you can do as usual. See, first row, second row, all this. Okay, Hungarian method you have to use. Step 1, step 2, reduce matrix, all that the same procedure. There is no change in the procedure. So but here you will get number of allocations is not equal to order of the matrix. Okay, hence the solution is not optimum. Fine. So this is the reduced matrix. Why? Number of allocations should be equal to order of matrix always. So what to do? You have to modify the reduced matrix by following the steps. Fine. Hence the solution is not optimal. What are the steps? You have to identify the least uncrossed element and you have to add that element to the double crossed elements. Okay. Fine. You have to subtract that element from uncrossed elements. All that procedure you have to follow. 3 steps that we have discussed in that professor's problem, I think. Fine. By doing all that, now finally you will get number of allocations is equal to order of the matrix. Okay. First thing is you have converted this into minimization form, then you have balanced it, then you have allocated by using the Hungarian method, that is applying step 1 and step 2. But you are seeing that number of allocations is not equal to order of matrix. Hence you have to improve the matrix. In other words, you have to modify the matrix MRM. For that you have to identify the least uncrossed elements, that is 1. You have to add this 1 to double crossed elements. You have to subtract this element from other uncrossed elements here, and single crossed elements you have to write as they are. Fine. After all that, okay, you will get this final status. So number of allocations is equal to order of matrix 1, 2, 3, 4, 5 or something like. Then you have to map like this, P1 to J1, P2 to all this. Fine. Then in the question it is given who is the spectator. So spectator means the boy who is assigned, the person who is assigned to a dummy girl. So here it is dummy, no, it is 0. Fine. So he is the spectator. P2, that is boy 2, is idle person, as he is not assigned with any goal. Fine. Now let us take a problem having alternate optimal solutions, so that all the special types will be discussed. Okay. So in this problem itself I have discussed 2 types of special cases. What are those? Conversion of maximization to minimization and balancing unbalanced to balanced type. Balancing an unbalanced problem. And of course this is a prohibited route, just have to leave it. Okay, that particular location you have to leave it. Sometimes in fact, okay, if you have zeros, what is the indication? You have the allocations. Okay, you have to allocate. You have more number of zeros, more number of solutions you will get. Okay, if you see this, if you look at this problem, this is row reduction, this is column reduction. After row reduction and column reduction, it is called reduced matrix, which is ready for allocations. Sometimes what may happen is none of the rows or none of the columns. You please note that none of the rows or none of the columns may have the single 0. Only in such case, okay, you have to sense or you have to observe that there is alternate optimal solution. You have to come to conclusion that when none of the rows or none of the columns are having single 0. More zeros means more alternatives, nothing else. Fine. Here that's what is happening. Okay, see, after first step and second step, no. So okay, so none of the rows or none of the columns are having single 0. Then what you have to do is one zero you have to ignore, and you have to allocate for the other one, and you have to go on. So in this process, no. So none of the rows or none of the columns are having single 0. So hence, okay, you have proceeded. For example, this one, in the first iteration, so 2 zeros you left, 2 zeros you left. Okay, 2 zeros you left. Here there was a single 0 you have allocated for this. Okay, then you have come to the second run, 2 zeros. Okay, single 0 you had, no. Okay, you have allocated for this. Now what is your observation? You see, here is, so 2 zeros, 2 zeros. None of the rows. Okay, if you come to the columns also, if none of the rows are having single 0, you have to go to the columns I said. But here in this stretch, what is happening? So this row also is having 2 zeros, this row also is having 2 zeros. This column also having 2 zeros, this column also is having 2 zeros. So what is your observation? None of the rows or none of the columns are having single 0. In that case, what you can do is, you can ignore this time being, you can allocate for this, then it will take the position. Then by default it will take the position. That is one solution. Okay. Or, so you may get a doubt, why you have to ignore this? Let me ignore this and check. That also I can do it. Okay, only this stretch, okay, please check it. Fine. So none of the rows or none of the columns are having single 0, no. So in the first this one, just you can ignore this and you can allocate So this will take allocation, this will take allocation. Or in the second one, instead of ignoring this, no, so let me ignore the first one and allocate for this. Then this will take position, this will take position. See, positions may be swapped, that's all. I mean, so you may get the alternative assignments, but the cost will be same. You please check it either by this assignment or by this assignment. Just to interchange these two, no. The cost of assignment is same, you can observe. The optimal cost is 1 plus 1 plus 1 plus 0 or something like, it is 3. So either by this or by this, okay. So that's what you can see, either this step or this step, okay. Assignment cost, alternate optimal solution, that is cost is same, fine. So this will get only when none of the rows or none of the columns are having single 0. You have to ignore one row wise or column wise, whatever it is. Then you have to allocate for the rest, and you can swap and check it. That's all. Fine. This is about alternative optimal solution. Now let us take a case study how we can apply the assignment problem in a realistic or so in general. The captain of Indian cricket team has to allocate 5 middle batting positions to 5 batsmen. Fine. Out of the available 6 who are all capable of to play at any of those middle positions, you are given with the average runs scored by each batsman at the specified positions, okay. So there are 6 batsmen and 5 persons. Of course, is unbalanced, no? You have to make it balanced by adding another position, that is dummy position with zeros. Okay, now you have to give the solution by using the Hungarian assignment method, HOM. Best batsman you have to assign to the best position by using the technique that you learned just now. Fine. There are 6 batsmen, 5 positions. Of course, one batsman will not be having the position because, okay, finally you will get that like a spectator in that boys and girls problem, because only 5 positions are there, but there are 6 batsmen. One batsman will become the idle. Fine. What you have to do, just to apply the method, no, you have to create one column, one position, then finally that position will be dummy only, of course. Fine. So just you can try this problem. So you can give the solution very easily for this kind of problem or any kind of problems. So which will be having the matrix form like this. Fine. So the captain requests you. What is the this one? What I mean analysis of this case is the captain requests you to suggest the battling order to see that the maximum runs are scored. How many runs can be expected to be scored by your arrangements? So to maximize, okay. So that's what you have to see. It is there are again 2 variations like that boys and girls problem only. So these are the runs, no, 58, 64, 60 and all. You have to maximize the number of runs. Okay, you will never. I mean, you are not supposed to minimize the runs. Okay, scored by the persons. Fine. So hence there are 2 variations again. One is unbalanced and one more is minimization. You have to convert this problem into minimization problem. Then you have to balance it also, then you have to proceed. That's all about this session. So I hope, okay, you have met with the objectives that were listed in the beginning, or outcomes or objectives. So first thing is formulation of an assignment problem, or to understand the structure of the assignment problem that we have discussed here itself, that is nature of the problem. Then also have discussed the assignment problem in 3 steps. Step 1, row reduction, column reduction. Step 3 is allocations. You have to allocate for zeros. Okay. Then step 4 also you may get maximum. Okay, that is when number of allocations is not equal to order of matrix. No. So then you have to modify the reduced matrix, that is called MRM. For that, okay, I have given simple 2 steps. So maximum 4 steps you will get. In regular problems, 3 steps only. That is step 1 row reduction, column reduction, step 2, step 3 allocations. In case, okay, if number of allocations is not equal to order of matrix, then it is not optimum. You have to go for step 4, that is modification. Fine. Then I have discussed about special cases, unbalanced. Okay, when number of rows is not equal to number of columns, you have to balance by dummy row or dummy column. Prohibited means just you have to skip that this one, dash or infinity you have to put. Maximization problem means you have to convert into minimization problem by subtracting all other elements from the highest element. Then finally we have discussed about alternate solution. If none of the rows or none of the columns are having single 0, so then it indicates the problem is having alternate optimal solution. So only you have to think that, okay, when none of the rows or none of the columns are having single 0, then okay, you can alternatively choose the assignments, but the answer will be same. Assignments will differ. That's all. Okay. So I take this opportunity to thank you one and all. Thank you. Take care and have a nice time.